I'm Pavithir V. Bharadwaj. Welcome to episode 29 of Genesis of Tomorrow. The following is going to be a conversation about quantum algorithms, quantum technology, artificial intelligence, mathematical first principles, the energy crisis, and more with Dr. Alexander Clark, a mathematician and educator. He is also the head of AI innovation and senior director of engineering at Next Trucking, and quantum algorithms and mathematics advisor at QDE L3C. Also, 95.2% of you watching this have not subscribed yet. So, if you get even the slightest bit of value from the show, please support us by clicking that subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. And we're rolling now.
All
Welcome
right.
to the show, Dr. Clark. It's lovely to have you here. And there are three, four main branches that I would like for you to speak upon, starting with your work and your interest. We can talk about those two parallelly or in different capacities to your liking. The second main thing that I want to discuss with you is the matter of mathematics and quantum algorithms, how both of these sort of complement one another, require one another, and you know, another aspect that I found very intriguing about was this excerpt from your bio, LinkedIn bio, which said that you are a mathematician and a teacher, and being a student, a perpetual student, enables you to be a better teacher. So I'd like for you to talk a little about that and innovation
Sure.
and all those things from the perspective of a teacher. And fourth being the matter of energy crisis, because as quickly and hastily we are moving forward with all these different technologies, we must cater to the questions that relate or pertain themselves to the challenges that they might pose simultaneously while giving us the benefits. So these are the three, four main things. And let's start by your personal journey, your interest, what you do, your work.
Um, I I think. Well, first. Thanks for having me. Uh, from the perspective of work, I think the thing that there's like a through line. When I was teaching constantly, I always said there's always kind of a through line. What are we really trying to accomplish here? And for my life, the through line is just how does mathematics apply into um, how does mathematics apply into things? I mean, just sort of said more broadly. So, for example, I have a 10-year-old and he's learning piano. He's very bright at math. And so when I sit down and I talk to him about the music theory and how this is mathematical, he does much better, right? And so it goes from music, it goes to computing. I like pure math, just, it's puzzles, it's chess games, it's Sudoku. For me, the through line of my life is mathematical thinking. That's how I go through the world, right? That's how it works. Even I like to be an amateur linguist, and I start at a completely unorthodox place, that is the grammar, because to me grammar is like an algebra, right? There's some set of rules about how you put together words and sentences and paragraphs and ideas, and then you add the words in later. So I even look at grammar in languages as an algebra. In a sense, it's not so literal. So anyway, that's kind of who I am. Um, And then what I do is all the mathematical things related to that. I like to, so I'm a referee for a mathematics journal. I work in a logistics company doing optimizations, forecasting, price predictions. I started a pair of companies, co-founded. Maybe you'll get to talk to my co-founder soon, in renewable energy, IP, computing, efficiency. There's even finance. So we're in that space looking at all the things that touch renewable energy. Um, so my work is a little bit various. I've worked in electricity trading, I've worked in credit, I've worked in quantum computing, I've worked in um, traditional data science role teaching. So just whatever mathematical thing happens where I can go solve it, that's where I go.
Two things. Firstly, being this, personally, I've noticed this sort of a recurrent pattern. People who are fluent in the language of maths are generally inclined towards understanding the semantics of linguistics. And why do you think that is? Do you feel that it is a recurrent pattern as well in mathematicians?
To some extent, yes. I think a big part of that historically is that there were essentially four languages of mathematics. There was French, there was German, there was Russian, and there was English. And so for the mathematicians to be able to communicate, they all had to learn a little bit. Even up until the point that I went to graduate school, so, and still in some places, one of the requirements to get your PhD is to be able to translate literature from another language into your home language, right? Although that is mostly been removed with Google Translate and the large language models doing a very good job of translations. But um, I think that many generations of mathematicians were forced to learn at least rudimentary grammar for another language. And I imagine a lot of them, not all, but a lot of them probably saw it the same way I did. There's some grammatical structure that once you break that down, the words just fall into place. A lot of the words in science and mathematics are shared, except in Polish. Polish has its own vocabulary. I can't read Polish at all, not even a little bit. They have their own word for functions and calculus and quantum mechanics. Everything is just completely Polish. But French is a lot closer to English, for example. Reading a French mathematics text is, it takes some effort, but um, the since the grammar of French and English are not so far apart and the terminology is quite close, it makes reading and translating a much easier mental task. So maybe that's what it is. My advisor, um, he's Ukrainian, but his family was Jewish, so he was fluent in Ukrainian, Russian, Hebrew, and then for whatever reason, Portuguese and Japanese and English and French as well. So so there's a bunch of polyglots floating around the mathematics circles.
The second thing that I picked up from your intro of sorts was how you were a very multi you on a professional front you were a very multifaceted individual, right? What, according to you, enables you to be able to, apart from just a keen interest and intrigue towards these domains, passion for the work that you're doing in all these fronts, what is something that enables you in more practical pragmatic sense to be able to do all of this while not maybe confining yourself into a particular definition or a box?
Um, so I had a friend back in undergraduate, one of the smartest individuals I ever met, and he came and stayed with me for a while in graduate school, and I asked him about a problem I was working on, and he'd never touched it and just started solving it. And that for me was kind of a moment. So I went off, I did my things, and he was staying at my home for that day, and I came back and he had solved half of my problem just afresh. He's like, oh, you know what? There's this other thing going on here that you weren't looking at. And so, um, to me, I sort of took that idea and said, well, the rules of mathematics they're really simple, right? From a perspective of algebra all the way down, like what you do in elementary and middle school. There's kind of just two rules. Don't divide by zero. That's not allowed. And then whatever you do on one side, you do on the other side. And then everything else just follows from logic. Of course, there are tricks, but part of the part of the fun is figuring out what those tricks are, using some trick that you know to solve another piece. I was told I went to a summer school in graduate school on the Riemannian geometry, which is not exactly my field of expertise, but the organizer said the problem that a lot of people have specifically mathematicians, is that they say, okay, well, I came up to a problem, I don't know how to solve it, so I'm going to go read whatever other thing. Sheaf cohomology is the example used. And you spend a year reading it and you learn the basics, and then you learn how to translate your problem into another form. You say, oh, well, I don't know how to solve it again. What you need to do is take your expertise and turn it into um, solving a problem in a unique way, right? That there's no prescription for that. There's no universal rule how you do that. It's just um, if you have an expertise in a particular problem, you can learn how to apply it in a lot of other different fields. And that's kind of my motivating drive. So, well, I know a couple of tricks, a couple of really deep mathematical tricks, only maybe three or four, but I see where they go into quantum computing. I see where they go into artificial intelligence. I see how it goes into pricing. I see how it goes into renewable energy. Um, so that's kind of my driving force to say, oh, well, I have this very, very, very tiny set of tools, but they're very powerful. I have four or five of these guys, maybe four tricks that I know, and I just apply them everywhere I can. And people say, well, how did you figure that out? So, well, I sat down and I worked on it really hard for a long time, and I failed a whole bunch of times. I really messed it up 30 times, 40 times, 80 times, and then I got it right, and I was happy. So it's not as straightforward. I think in school, especially in mathematics and science, we're told that there's a right answer. But as soon as you get up above undergraduate level, you realize we basically just only know that tiny little amount, and that's why we taught it, because that's all we know. We know very little, and really half of the fun of being a scientist and a mathematician and a programmer is to figure out problems that people haven't solved yet.
For
That's
you,
the
it was these
that's
three,
that's my
four.
trick.
Yeah. Hmm. Hmm. For you, it was these three, four different set of tools or equipments in the study of mathematics that you had devoted so much of your time and effort into honing, essentially. How does an individual figure out which set of tools they can use to devote their time and effort to, and then in the process also how can they go about honing those set of tools? Because it can be it's subjective for people, for different people, right? For you, you were able to figure this out, and I'd love for you to touch upon how you realized this, that it was probably mathematics, and then it was these specific things that I'm working on. Okay, there's something that is unique, and I think it might be something very unique that may set me apart from these bunch of other guys who are essentially working in the same field. How do you do that? How does one go on to do that?
Again, I think a there's not a given rule for how this works. I'll give you a couple of like highlights from my life, that things that like changed my mind. Um, the first was when I took quantum mechanics in undergraduate. One of my degrees is in physics, and um, for listeners who don't have a technical background, I'll try to make it as simple as possible. The the harmonic oscillator, so harmonic motion on a spring. When you translate this into quantum mechanics, it becomes important partly because that's how electrons move around the nucleus of an atom. Okay, so you have a nucleus here, and the electrons moving back and forth. Of course, it's going in 3 dimensions, but it's a spring in 1 dimension, and in every dimension, it's kind of like a spring. So we have a quantum mechanical model of that, and that's one of the very few models in quantum mechanics that actually has a solution, like a solution. You can actually really write it down and solve it explicitly. And the way that I was shown to solve this basically ended up being factoring uh, a difference of squares. And this just completely blew my mind, that you're treating a derivative like an algebraic entity, but it doesn't work with x, right? It doesn't commute. This just like absolutely blew my mind. And there's this little tiny trick where you say, oh, the solution is just counting numbers. starting at zero. That's the solution. And so we took this really complex problem, which is every atom in the whole universe follows this rule, and they solved it in like a few lines, and this just blew my mind. I was, wow, what can't you apply this to? And so I started really taking that particular trick and just applying it everywhere I possibly could. Um, that was my trick that I learned. I used it to classify time series. I've used it for making time series predictions. I used it to apply this into quantum optics, where you like bend the oscillator and you sort of perturb it into this other. I use this thing everywhere. I just use this everywhere, everywhere. I love this thing. And that was kind of like my first amazing moment. I'm 20 years old and someone shows me, oh, you just treat um, all these functions and things in calculus like you did in seventh grade. It just completely blew my mind, and I love the quantum harmonic oscillator. Just absolutely love it. That's one of my tools. Um, so the second thing is, I mean, everyone's probably heard this story, but it's actually there's a book called The Wisdom of Crowds by James Surowiecki. He starts with a story about Francis Galton. Galton later got in a little bit of trouble because of his views on eugenics, but before that, he had this really interesting idea in, I believe it was 1906, in West Essex County in England. There was a competition at a fair to guess the weight of a bull. Okay, and so Galton was really obsessed with measuring things. Right, and this is kind of before we had developed statistics proper. Right, it was sort of in its nascent stages. So he asked a group of 50 experts to guess the weight of this bull, and he asked all the rest of the people at the fair to guess the weight of this bull. And over the course of 2 days, he collected almost 800 answers from the general populace and about 50 answers from the experts. And the experts guessed 1,350 pounds. Okay. And the bull turned out to be 1,298 pounds. They're off by 52 pounds. Like, really an exceptionally good guess for the experts. But the crowd, there are people guessing like 1,000 pounds, or people guessing 200,000 pounds, all sorts of stuff. Their average came out to 1,297. They were off by less than 1/10 of 1%. And that idea made me think, okay. So the book actually describes it really, really well. But what you need, if you have a whole bunch of independent observers, and you sort of average their answers, generally it does better than almost anyone in the crowd. Like, that's probably close to the single best answer. It might be top two or three, but your best bet, if you have like independent people guessing independently, you're going to get really close to the right answer. And so now I apply this into pricing. That's how I built a stock predictor. Um, and it did okay, but it survived a crash, right? We made a little bit of money in a crash. And the way that I did this is I just asked so many different predictors what they think is going to happen with a bunch of different stocks. I asked many, 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 many different predictions to predict the stock price. And usually they come across as like no change. But if you have one that on average, you have like hundreds of predictions saying on average this thing is going to go up by 0.5% this week, that was a signal that I thought was worth watching. Okay. And so in pricing freight now, what I do is I price truckloads going across the United States. I do this. I ask 800 different AIs to predict all of the prices together, and I take a weighted sum of their guesses, and that's how I get my prices. What information I put into those guesses, I don't tell, because that's that's proprietary. But the basic answer is I ask a bunch of different AIs independently, as if they've never talked to each other, and I just record all the answers separately and take a guess. Right? So that was sort of like my second big trick. Um, yeah, and then the other tricks are basically, look, there's a lot of there's a lot of randomness and uncertainty in the world. There's just a lot of it. And I think saying things like everything happens for a reason usually holds us back from being able to solve what happened. Sometimes, very often, most of the time, it's just random coincidence. And I know that's not fun because conspiracy theories are so fun. They're so fun. It's just they end up not being true because it was just coincidence, usually. But man, they're fun. They are fun, but that doesn't usually help solve a problem. Sometimes it's just a fluke. Usually it's just a fluke.
It's really interesting how what starts off as a very theoretical matter often bleeds out into these different pipelines of practical applications that just change everything. The way that normalcy is perceived, the normal reality is perceived, it gets changed. Like all the technology that we have today around us ourselves, artificial intelligence like ChatGPT, LLMs, for a normal person, they type in a prompt and they are able to just generate the answer to everything, each and every of their questions. Have those models do their work. But at the crux of all of it is a very mathematical computation, a very nuanced, complex mathematical computation that goes on to do all of this. And that holds true for all of these different facets of science and technology. What, in your opinion, currently is the most significant piece of technology for humanity at large, in whatever regard that may be?
Mm. Well, I mean, without plugging my own company too much, what we're going at right now is um, I've been interested in renewable energy for a very, very long time. But renewable energy has, of course, some problems. One, intermittency. Two, generation capacity. Three, grid capacity. There's a lot of things that are happening around renewable energy. And so, one of the other tools in my bag is to say that's a problem. Oh, no, 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 no. That's where the opportunity is as a business. Okay, and so what we're trying to do, when my company Interjuice, we're trying to develop this idea called energy intelligence, right? And so our tagline is that there's no AI without EI, right? The idea being this: current AI, especially large language models, are drawing so much power. It's much more than EVs, and it's much more than quantum computing. AI is right now a big problem in the energy sector, right? And from my perspective, there are three computational resources that we really should pay attention to. There's speed, there's memory usage, and now because we have computers that are so large, you look at Frontier at Oak Ridge National Lab and Sequoia and all these like massive Titan 2, these massive computers, it's the energy consumption. How much energy does it cost to actually run the computer? Right now, Microsoft and OpenAI are trying to they're reopening nuclear facilities, right? Which, from the perspective of carbon emissions, is fine. But the grid is not balanced. The cables themselves, the physical wires, don't always have enough capacity to carry all that energy back and forth. And so, um, the most significant technology right now at the moment is AI, but not large language models necessarily. It's the AI involved in optimizing grid capacity, right? There's reinforcement learning. I think reinforcement learning, generally speaking, right? This I'm not talking about just solving chess, right? But reinforcement learning as a general idea is the most significant technology that we're seeing right now. Um, and what we're trying to do is use reinforcement learning specifically to solve some optimal power flow problems to make sure that the grid is balanced, that we have, you know, there are storage issues, there are distribution issues, there's optimization issues, right? The sun is providing us more than we need in terms of power, raw power, but we only get it for part of the day or we have to store it. Now the storage has other problems with, do you do it in a battery? Do you do it mechanically? Do you do it in water? Do you put it in a gravity battery, pump it uphill? What do you do to store that energy? And then how do you release it? Where are your losses? Where are your gains? All of these problems are very difficult. And so when you really look at the mathematical problem of solving this power flow, it's extremely difficult. And so without reinforcement learning, it's an intractable problem. The way that um, the way the energy, at least pricing and power flow, has been done for a long time is that they relax this idea of alternating current down to direct current. So there's two problems. There's one called the ACOPF, which that's the alternating current optimal power flow. That is a very difficult problem. It's not tractable in finite time by brute force. It's just not. You cannot solve it. It's non-convex, non-linear, multi hundreds of variables. Like cursor dimensionality. You name any problem that you have in solving mathematics problems, ACOPF has that problem. Different topology, time-based graph networks, directional graph networks, acyclic graphs, cyclic graphs, like degenerate spectra, whatever problem you want, ACOPF has that for you. Now, the way that is actually done in practice, at least in the United States, Canada, Mexico, is they relax this to solve what's called the DC OPF. That's the direct current optimal power flow. That is solvable. It's difficult, and it gives a good approximation, but only at like a small scale. That one you can actually solve with traditional operations research. Okay, so the goal is to sort of decentralize a lot of power stations. I think having a centralized power grid is difficult. So there are a couple of problems. Where do you optimally put these microgrids? And then how do you balance those microgrids? And then how do you have the microgrids talk to each other? Right? So we're basically trying to build up an entirely new style of grid, one in which each little miniature grid can actually have the ACOPF solved. But even in these little bundles, these little microgrids, ACOPF is still difficult. And so, right, reinforcement learning is still needed to at least get an approximate solution. You can get better than DCOPF because you can give this as like an initial solution. You can say, start your guessing with this, right? And don't give me anything worse than that, right? This is one of the tricks that you have in optimization. Like if you have a pretty good first guess, start there and let the optimizer go and say, don't return me anything that's worse than this one. And it's one of my other like bags of tricks, is like getting a good first guess. So there, I think AI, but not in the way that most people think about it. I think AI for the purpose of EI is our most significant technological thing right now. Sorry, that was a little long-winded, but
How do you think? No, I think it was a perfect explanation for the kind of question that I posed. I posed a very abstract question, and you were able to give a very an answer that was very much in touch with reality, the current reality, ground reality, and I appreciate that. Uh, Another aspect that this discussion would seemingly seep into is of AI is constantly being talked about to sooner than later start manifesting itself into our physical reality. We started off with these chatbots, and there now being talks going on around about physical AI, right? Robots. How do you think the society at a very fundamental level is going to change or get tweaked around? How the dynamics between people themselves are going to change in these coming years?
um, it's not a super satisfying answer. But the real answer is I have no idea. I just don't know at all. But my best guess is this. Again, I think we're a little bit sleeping on reinforcement learning. Reinforcement learning is where robotics is going to make the biggest leaps, right? So we are going to teach robots to do things better, and that's not through large language models. Recently, there's been a lot of talk of small language models, and I'm looking at something like Mathematica, Wolfram Alpha. All right, Wolfram's been in the game of AI for a long time, but they're doing specifically computer algebra systems and solvers and optimizations. Right, I think they've added in a chat to Wolfram Alpha at this point, which is interesting, but they don't have to know like the history of India, right? That's not what this language model does. This language model knows as much about science as it can, and it doesn't have much on the history of the Indus Valley, right? It's not going to tell you anything about which dinosaurs and tea leaves were in Sri Lanka. This is not its purpose. So I think combining these things, small language models, where you have kind of, it's just sort of like a corporate hierarchy again. You have one language model that sort of discriminates which smaller language model it needs to talk to, and then that one sort of does its little expertise. I think this is possible, and so it won't get to artificial general intelligence, and there's some reasons I have for this, but it will be indistinguishable from black magic for most of us. But robotics are going to be able to work, and I think this is from reinforcement learning. Boston Dynamics always puts out these videos that sort of shock us, like, oh look, it's kicking this dog-like thing, and this dog-like thing is getting back up or keeping its balance. And I saw a video of someone who designed a motorcycle with a big shell around it that got hit by a car, and the motorcycle maintained its balance. It's like, oh, that's the classic problem. That's why it's the cart pole balancing, right? It's the classic problem in reinforcement learning, the one that you can just load up in a MATLAB script. So I think that's going to be applied in a lot more areas than we're willing to think. And large language models, I think, are going to top out. And I think this is for two reasons. One, the energy consumption is too much. And until we have the energy intelligence to balance that out, we've sort of topped it out. Two is that there's just no more data for it to ingest. If it's ingested all of Wikipedia and all of Twitter and all of Facebook and all of the social media networks and listen to all the podcasts, and it still can't figure out stuff, well, that's it. That's its top. Until we figure out some new algorithms, this is the best that we're going to get out of large language models.
What about algorithms? I think even on the quantum computational front, there has been advancement in terms of different facets of the technology, but algorithmic advancement to research, you do not often get to see big leaps in there. And sure, because of the intrinsic difficulty of the subject, but again, what is the algorithmic side of things? The classical computation, but as well as quantum stuff.
What's the algorithmic side of quantum computing?
Essentially, yes.
That will keep increasing. The big, in my opinion, the biggest problem facing quantum computing is that most of the programmers never studied quantum mechanics, and so they don't understand that there's like a real physical limitation to what quantum computers can do. Recently, I sit on some IEEE subgroups around quantum cybersecurity, and we had a discussion last week about there's research about thermal dissipation, meaning that researchers are now trying to figure out what is the limit of the amount of qubits that could actually be entangled before they dissipate. Right, and this is something my co-author and coworker Kiefer Sharkey has talked about several times. That the thing that her trick, like my quantum harmonic oscillator, her trick is the Born-Oppenheimer approximation. Right? And it basically says this, simplest explanation. In high school physics, we were told total energy is kinetic energy plus potential energy, right? And that's how it works in quantum mechanics, except that at a low level, you have a couple of other things. You have spin and rotation energy and vibrational energy and a couple of other things in chemicals. So um, when you're actually building, so the Born-Oppenheim approximation just says that the energy is just simply the sum of kinetic plus potential plus spin plus vibrational plus there's like 6 energies that you can add up, and that's the sum, and it just sum them, just add them. When you start like hitting these little guys with lasers, you're changing the rotational energy, adding more and more energy. When an electron comes out of a ground state into an excited state, the energies are no longer just a summation. They're approximately a summation. There's some nonlinear interaction that we don't know. It's not analytic. There's some nonlinear interaction that we don't know, right? And when you have enough qubits and you put enough rotational energy into a system, these nonlinearities start taking over, and that's not well understood. So there's some physical limit, and it's not yet known, to how many qubits can actually be entangled. There is a physical limit. It's not yet known, and it's a lot smaller than I think a lot of people expect it to be. My best estimation now is that Shor's algorithm, even if implemented perfectly, wouldn't be able to handle our current largest known prime. All right, so our current largest known prime is 2 to the huge prime number, 136 million something 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 minus 1. Okay, take that number and add 2 to it. So 2 to the something 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 plus 1. Can Shor's algorithm solve the discrete log on that and then factor it? I think it's actually physically out of bounds for this to ever happen. Not that I don't want it to happen, I just don't think it's possible. And it might not be that prime, but there's some prime kind of in that region where when you try to put that many qubits together, the energy levels get to a state where the nonlinearities take over, and we don't understand that yet. These are not known answers, right? I'm not telling you what they are because I don't know myself, but there's a limit, and we haven't discovered it yet. Most quantum computing companies, especially the ones that have stock options, are ignoring this completely and just saying, no, we're going to be able to solve it. We're going to do universal quantum computing is coming by 2030. And I'm taking a huge bet against that. I'm taking a very large bet against universal quantum computation ever happening in that format. I think there are much more realistic ways in which quantum computing is going to affect us.
What exactly are those ways that you think that quantum computing will be able to affect the society at large?
There's a couple pieces. A few years ago, I was talking to Q and Co., which then merged with Pascal. They're in Europe, Netherlands, France, and they had built an algorithm called differentiable quantum circuits. And so the idea is that they can sort of do a gradient, an automatic differentiation quickly. And so what they were trying to do is say, okay, we have all these classical algorithms, but here's this one piece that takes a long time, and we can write it in a very short quantum circuit. Right? Variational quantum eigensolvers is a good one. That's a great example of how hybridized computing is going to work. So, think of like an algorithm, being step by step, right? What the really clever engineers are trying to figure out is like, oh, right here in step 6, that one we can pull out, run a quantum subroutine, and put it back in. So the algorithm actually shrinks to this. You still have to do mostly classical stuff, but there are a couple steps in there where you can hybridize it. And the the difficulty of the quantum computation is such that it is within physical limits. That's the trick. So the real trick is to figure out what are those subroutines that can be quantized that actually work. Again, not a known question, but this is not out of bounds, right? This is within the physical limits of actually being able to happen. And I've seen a few algorithms where this actually works. Quantum computers are not quite fault tolerant enough yet to handle that in large scale, but I think they will be. We're figuring out better error correction techniques. Um, it's just there's some physical barrier which we don't know. And so before we get that, we're going to have to get these hybridized computing going. The second piece that I know is going to happen, I'm here in Chicago, there is quantum communication. Quantum communication and networking is happening. Um, Securing networks from physical attacks using quantum mechanics, also possible. And the real advantage here is that quantum mechanical systems are actually random. But the real advantage is that entanglement is not needed, right? So if you entangle two qubits, you've reduced what the possibilities of their measurement is, right? So think of it this way. I have two coins and they're going to match, right? So the heads and tails is not a possibility and tails and heads is not a possibility. That actually hurts you in encryption because you give the attacker, you've cut the search space down in half. So what you really want to do is just flip a bunch of coins, right? That's single qubits. If you can send out a system of like 1,000 qubits that are truly random, no one was ever going to crack this. The only thing they can do is just cut the communication off, right? So since the entanglement of a lot of qubits is not necessary, in fact, a hindrance to this type of encryption, that can actually happen. We do know how to build a single qubit. We really know how to do that. I had a kid do it in lab one time for a quantum computing class. He built a single qubit in the physics lab as an undergraduate. So this is possible, right? This particular uh, quantum communication will happen. Hybridized quantum computing will happen. Universal quantum computing will not.
Hmm. You also said that it's highly unlikely for AGI to, at least anytime soon, to be able to materialize into the kind of reality that it's often perceived with. What are your reasons for it? And
I mean, the
how
easiest,
can,
I go back to this, my,
yeah.
again, I hope you talked to my co-founder, Mike Davis.
Hmm,
Um,
hmm,
his tagline is "There's no AI without EI." Part of it is that we don't understand how to run the computers efficiently enough from an energy perspective. Right, the AI is it's burning up too much electricity, and right, the amount of power that you would need to have something generative, like actually artificial general intelligence. Let's put some limits on this. What does this mean? Okay, and I think from an energy efficiency perspective, I want a computer to be able to solve a problem, an abstract problem, faster and with less energy and with less memory than a human. Right? Let's look at Stockfish or Houdini or AlphaZero, these chess engines. Right? Their transposition tables like 32 terabytes. We don't have that kind of chess memory. Right? Can a chess engine beat me having played only a few hundred games? That's the question, right? I've played a few hundred games of chess in my life. Can a computer that's only played a few hundred games of chess beat me using less energy than my own brain? Because I don't think so. Right, now apply this to general. So suppose that you restrict a computer to only learning what one human could have learned in a lifetime. Can that computer outperform a human on less energy? I think there's just no possible way. Our brains are just way too efficient and we don't understand them well enough, especially the energy consumption. Right, Vaclav Smil in Canada has some really excellent books. One is called Energy and Civilization, where he basically just maps out how much energy our brains needed to survive and why he goes all the way back to like why we chose corn and wheat as our staples because of the energy density they delivered per per weight. Right. This is so super interesting book. I highly recommend. Um, but there are a couple questions I want to say around AGI. One is the question I really like to go is, can this solve the Collat's conjecture? Right, and Collat's conjecture is just some stupid problem. It's the 3n+1 problem, if you're unaware of it. The question is simply this. Take any integer bigger than 1. If it's even, divide it by 2. If it's odd, multiply by 3 and add 1. So 5 becomes 16. 16 becomes 8. Iterate this. Eventually, you're going to hit 1 at some point in your... Not checkable. You can't check all infinity integers. Right? It's not possible to check all infinity integers. In order to resolve this, you either have to find some cycle of integers that you apply this function a bunch of times and it comes back on itself. No one has been found. Or you have to give some argument for why all infinity integers eventually collapse down to 1. There's no amount of data. There is no amount of data that can ever resolve this. Right? So the first litmus test for AGI is, can it resolve some question for which no amount of data is sufficient? Something that humans haven't resolved. Can it resolve the twin primes conjecture? Can it solve Ramsey numbers? Right? Can it give me a general... There are some problems that we know to be computationally extremely complex, like super exponential. Can it solve one of these things? Because the amount of data that it would need outpaces like the number of electrons in the observable universe at factorial. Right? Until a computer can solve any one of these particular things, I'm not even willing to enter the discussion of, is it generally intelligent? That's kind of my litmus test. It has to be able to resolve something for which no amount of data is sufficient. And there's a lot of good questions just on integers.
Hmm. But one
So
aspect to it is, yes,
go ahead, please.
yeah, yeah. One aspect to is that at some very specific tasks like creativity, decision making, and it's happening with generative AI and all of these things, the large concept models, especially the LCMs. Does artificial intelligence really need to reach that level of sentience to be able to surpass humans at the the tasks which will essentially make us obsolete? What I'm trying to say is, if unemployment is one of the aspects that gets thrown around when there's a discussion about how the society in which AI becomes a lot more prevalent and advanced. Do you think that AI actually needs to reach that kind of uh, level of intelligence where it's able to solve w- problems that need an infinite amount of data to make humans obsolete?
I don't know. I'm betting against, and that's not from a self-preservation perspective. That's just trying to actually calculate the energy needed to do such a thing. Right? I think from an energy perspective, it's unlikely. I don't want to say no because there are people who are much smarter than I, all working toward this particular goal. And so, you know, algorithmic breakthroughs happen from time to time. But until such like an extraordinary algorithmic breakthrough happens, I don't see that happening. I see specialized AI actually performing a lot of tasks. Right? Being in logistics, I see, for example, self-driving cars is a little bit too much to ask in general, but for long shipping routes or long train routes, think about the train system in India, right? You could send a train going fairly slow overnight on a track and just have it, communicate with other signals. Same thing could happen in the United States. We have a lot of roads, interstates, motorways, where you could sort of dedicate a lane for long haul trucks to go, right? So there's like some autonomy that can actually happen. The difficulty comes in like getting the truck to actually park itself in a warehouse, getting a train into a berth, right? You need some human assistance for unloading, uploading, doing what we call last mile logistics in the United States, right? And so there's some idea that it could happen this way. It's one of the projects I'm working on for the company I work for now is called Batch Freight. Um, you can have a driver drive from a warehouse or a port onto a major motorway, and then let the truck take off on its dedicated lane by itself. It can drive through the night, no problem. And then when it gets to its next destination, so Los Angeles to Chicago, that's a long, long, long drive. It takes a driver several days to do this. Well, you could set a truck that goes in its own autonomous lane, and then one of my coworkers comes and picks it up in Chicago. Right? That's feasible. Is that generally intelligent? No, but it's good automation, and it saves a lot of effort. Right? You could teach a truck to drive in a straight line quite easily. Right? So like just stay within these lines. I mean, I've seen kids do it with a little Arduino. They just get a little sensor. The sensor just senses where the line is, and it just tries to stay on this line. You can do it. I saw a 13-year-old kid do it with an Arduino. Right? Certainly, big logistics companies that have a lot of money, DHLs and FedExes, could figure out how to do this for a truck.
Okay, probably tweaking the question a bit. How do you think people can, especially the people who are in the domain of STEM, essentially science or technology, academia or industry, how can they stay relevant in the age where things are becoming much more convenient to just multitask with the help of artificial intelligence and these models?
Well, I think this is from my stock trading. The one thing that you need to know is that the surest way to fail, the only way to actually fail, is to stick some system and stick with it no matter what. Don't deviate from the system. It just I'm always just gonna go long on my stocks. You're going to die. If any of these stocks are, that's it. There's no like guarantee in uncertainty. Now, pull this back to what I saw in my mathematics colleagues. A lot of them were unwilling to break out even of their very narrow disciplines to try to discuss a problem with me in a related field. Right? I study pure geometry. I don't want to study a little bit of algebra added to it. I don't want functional analysis. I just want this thing that I know. Um, the same thing happens for a lot of people in STEM. They pick a path and they want to stay on that path and they don't want to deviate. Technology doesn't allow us this. So we go all the way back to Prometheus. Prometheus took the fire, right? Um, what does fire do for us? Well, it cooks our food. It keeps us safe. It made sure that our life expectancies go way up. It also burns down our houses and our forests. So come further along. Um, Radio, television, automobiles, bicycles, all sorts of technologies have caused our lives to be easier, and they've caused a new set of problems. And like we said earlier, those new sets of problems where the opportunity is. Right? So each new technology sort of diverges our path, right? We have these other things that are solved for us and we don't have to worry about them anymore. Right? For example, these large language models do a really, really, really good job of just summarizing. A look at some articles. Like, can you give me a 2-paragraph summary of this article? That saves me a lot of time. They can just give me a little summary, and if it's worth my time to go investigate those pieces, great. So the summary game is mostly done. Fine. But as we get better and better language models, we're going to see more ideas come up. Think about YouTube, Instagram, Snapchat, whatever. We have content creators. If you had told me in high school, just me, that content creation was going to be a thing, I would have laughed. I go back and tell my parents that someone would be a web developer, someone would do this language called JavaScript, and they would get paid money to write a language called JavaScript. They would have, what are you talking about? It doesn't make any sense. So how do you stay relevant? There are going to be new opportunities that show up. As each technology keeps arising, we get new opportunities. What are they? I don't know. I have no idea. But stay on your toes. You have to try them. If you take the problems that you know, apply them into these new fields that opened up. These new fields, no one's ever seen them. So you have kind of first mover advantage. So for people in STEM, you really want to be this first mover advantage, right? This is kind of the way that Tesla did with electric cars. They have this plug standard, and then everyone else has a different plug standard, right? But before it got patented, before anything happened, like Tesla had this first mover advantage. Now everyone wants to get onto their charging standard. At least this is how it's playing out in the United States. We have basically Tesla and everyone else's. Right? That's how that particular thing works. Well, same thing with large language models, quantum computing, whatever energy intelligence. If you see as a new problem arises, that you should start thinking this is where the opportunity is. Or the opportunity is in solving the problem, not in like, oh my gosh, I'm going to get beat up again. Of course you're going to get beat up again. That's how technology works. It solved some problem for you, but it opened up a different one. The the way to stay relevant is to go find out how to solve that new problem. And no universal prescription, but that's how it works.
If you had to give, from all that you know, from all that you've spent your years studying about the different mathematical formulations, how would you describe existence? Define it if you had to.
Um, Actually, I just read recently. Carlos Kuhn is a good friend of mine. He's Australian. He just wrote a very little book called Echoes of Existence, and and the very first chapter, um, he gives a definition of God, and I'll put this in quotes for the agnostics amongst us. But he describes this as God equals the sum of all information at all times, right? Information on one axis and times at another axis, and I think like that's a really interesting way of doing it. It's just almost like St. Augustine's ontological argument, where you say, well, it's just the sum of all the informations, right? My family is Druze, which is a small ethno-religious minority, and their conception of the God is the universal mind. And so, um, even though I'm not actively practicing in that I think is kind of the right idea, right? That particular bit, I go like, there is a universal mind. So the sum of all of the things, including abstract ideas and stuff that didn't exist and stuff that never will exist, that's existence, right? I mean, it's a little bit self-contradictory, but that's kind of the beauty of it, right? Without getting spiritual, it's like just all the sum of all abstract ideas across all time, which itself is an abstract idea. That is what existence is. How do we navigate it? Again, don't know. I spent a year in India doing a postdoc, and people ask me about it. And you being there, I've told people the thing about India is that there are 8 billion different Indias. Every person is going to have his or her own unique India. They will see it in a completely different way. There's a different level of this country for everyone, right? India is not a thing. India is a thing for each individual person. Same with America. Same with any land. But existence is that. There's not one existence. There's the sum of all the existences together, right? So that's a little bit ethereal and more abstract than I generally like to go. But that's kind of it. It's just the sum of all the experiences all put together. That's what existence is.
Really interesting. Uh, what really struck me while you were telling me this is, there was this aspect of Hindu philosophy that goes on to talk about aham brahmasmi. It essentially talks about being one with the universe and the universe being one with you. And what it goes on to elaborate is the definition of God uh, being just that. It's like a total summation of all that there of all that you know and all that there is to know relative to each and every single individual that there is and thing that there is. So that and the best part about this line of thinking is that you do not have to be confined by any particular notion of that may have been imposed on you or that you might be imposing upon your own self. It structures the concept of existence in a way where you have a fundamental basis already that you can build upon, right? So all the knowledge that you already have, it somewhere is being verified, sort of like what you know is not, you aren't clueless, right? Because umpteen times the notion of believing in god, people take it the wrong way in the kind of sense that science and the notion of god cannot go together. And the definition that you gave essentially just talks about what science is trying to describe: information
Mm.
in its totality. So that's
Yeah, and so
I really found that interesting. Hmm.
I like so Carlos. I think he says that this is the philosophy of spiritism, which I hadn't heard of. But I think this gives an easy way to say, well, you can be agnostic and atheist and spiritual kind of all the time. It just sort of depends on what you do. I had a friend who was a priest many years ago, and there's a saying in the United States is I'm spiritual but not religious. And he said, well, religion is just what you do with your spirituality. That's all it is. I think, oh, that's a clever turn of phrase. So that opens the door for agnostics and atheists to also be spiritual in that particular way. So um, it this idea of the summation of all informations over all time in both directions, it kind of opens the door to say, well, there is existence and then there's not, and so wherever you fall on this is valid, right? I guess that's kind of the point. My own grandmother said that she was actually a believer of the Druze faith, and she said, the idea that if you want to accept that the God is like the creator of everything, it shouldn't be such a stretch to believe that this God can present itself in whatever form to whomever at any time. So the existence of other religions to her made perfectly good sense, up to and including not believing in anything at all. Right? That all made perfectly good sense. The atheists are those to whom God is not presented in any way. Right? Hindus are those for whom the Brahma have been presented in this way. And so I always thought like that was also a really good way of sort of like, everyone has their own thing. Right? And when I was in India, I thought about this a lot because there's not one India. There's 8 billion Indias. Each person experiences it for himself or herself. Um, one of the beautiful things about mathematics is that there is kind of like this is a thing that can kind of pull us back together. As long as we agree on some axioms, we're back in it. Spirituality is a different field that I don't play in too much because it's too abstract. Mathematics has some rules, like don't divide by zero and keep the two sides equal. That's kind of the rules. Spirituality is a totally different subject.
To close out this particular aspect of the discussion, how does, in your understanding, from a purely mathematical sense, in what way will mathematics be able to describe the universe and existence?
I don't have a good answer for it. I think this goes back to the discussion: is mathematics invented or discovered? I don't have a good answer for that. I think of it as discovered, but I don't know. I'm agnostic on that too, right? I don't know. Maybe I mean, what's the good compromise is God invented the integers, and you just stop there. And there's an old Russian Orthodox saying, this comes from Anna Karenina right at the end. We know where God is, we don't know where God isn't. Because one of the main characters, Lev in Anna Karenina, is like he doesn't believe in anything at all, but his wife does. She wants to be like a good Orthodox Christian, and so they basically end up telling, well, all that the Orthodox Church says. I mean, this is a paraphrase, of course. It's like we just know where God is. We don't know where God isn't. Right? And so, from a mathematics perspective, um, I tend to believe that mathematics is discovered, but I don't know. I don't have any numerical evidence one way or another. it's it's the idea that I'm sorry to drop a lot of books on you. I've been reading a lot in the last year, and there's like a lot of ideas just keep coming back in my work. Zen and the Art of Motorcycle Maintenance. Persig says the problem with the scientific method is that there's no scientific method for creating a hypothesis. That's a pure act of creativity. Once you have the hypothesis, you know what the method does. But how do you create a hypothesis? There's not a method for that.
I say it a lot, but and I really believe that science, what it's often taken to be as this very, from the outside perspective, this very monotonous, mechanistic entity. It isn't that. It's a highly, extremely creative and spontaneous thing that just comes about, flows into, seeps into.
Yeah, I agree. I think mathematics. I think living is this, right? You have some rules, but how you get to those rules and what you do with them is completely up to an act of creativity.
Coming to the culmination of the episode, Dr. Clark, what would be your word to humanity at large?
Mm, I think that at least the where I am at present in my particular life is that go back to early in the episode. Conspiracy theories are fun, but they're usually just coincidence. And I think the fun, sort of the fun of living, is to experience all these random events. There's lots of randomness, lots of uncertainty, lots of chaos, and kind of the fun of living is experiencing that, whatever that means. I'll give some examples just, and then we can close it out. I've run on way too long for your listeners. You have to cut it up in 2 episodes for them. Um, the During COVID, I lost several jobs. Right, one company went under. One company was a terribly bad fit. One company was reducing staff. It was just like I got fired a bunch of times, or lost a job, or the company went under, or I just wanted to leave. And when I was younger, like that level of uncertainty was really not acceptable to me. But every time I had to change jobs, I went up, and I had like a whole wealth of experiences to take with me to the next job. Right. And so every job change actually was a big improvement, even though it didn't feel like it at the time. It was nerve wracking and it was scary. And I think for people in your 20s, you need to get fired a couple of times. Like, I think this really does you a lot of good to get fired a couple of times and like have to re-find your footing. Um, I learned that way too late in life, but um, I really think a lot of the fun in living is to experience all these crazy uncertainties and sort of navigate it the best you can. Right? This is parenting. Parenting is just all about this. Like, just what chaos is coming at you today. This is what being a parent is. Um, and it's a lot of fun, and it's frustrating, and it's saddening, and it's like angering, and it's all of the emotions all at once, and it's just a lot of chaos. And um, how you deal with this, basically, this is the definition of your personage. How you deal with the chaos coming at you. right? People say like it's not if you get knocked down, it's if you get back up again. It's that sort of idea. There's just a lot of there's just a lot of uncertainty coming at us at all times from every direction, and that is living. Like, how do you deal with this? Like, if you're like just too risk averse, nothing happens, right? So here's the through line. Here's the through line for living. No risk really means no reward. That is just absolutely certain. That's like one of the rules of algebra. No risk means no reward. But repeated high risk also probably means certain ruin. There is a sweet spot for the amount of risk you need to take. And that changes for every person. Every person is going to have a different level of risk tolerance, right? I'm a little bit lower, but you have to find that sweet spot. However that works for you. I don't know. I can't prescribe for anyone other than myself. Like, what is the appropriate amount of risk to take in life? But that's where it is. When you find that sweet spot of like the ratio of risk to reward, then you've really made it. And that might be staying in academia to not take a high paying job, and that might be going to take a high paying job and not getting the academic credentials you want, right? That could be having a kid, that's really risky, or it could be not having a kid. There's, you know, everything is a risk and it has some related payoff or not, or ruin. So living is finding that sweet spot. Where is it? This is probably too little, this is probably too much.
Dr. Clark, thank you so very much for this episode. It was
Thank you very
I
much for
would
having
like
me
to
on.
say
I'm
it was
sorry I ran a little
profound,
bit long.
but it is completely fine. It is completely fine. And as much as I would like to say that it's profound, I think it was extremely explicit. I mean, you were very explicit in terms of the kind of message that you wanted to convey with each and every answer that you were giving about, and I really really enjoyed that thoroughly.
Thank you very much. This was a lot of fun for me.